Okay, in this section, we're going to do some curve sketching. And so basically, we're just going to use the idea of the first derivative, which tells us about increasing and decreasing. And we're also going to use the idea of the second derivative, which tells us about the curvature. We're going to use those things to help us sketch the curve. Now we're looking at the function x to the fourth minus 16x squared. Now we could just plot some points and we get kind of an idea of what the picture is supposed to look like. But if we want to know exactly where all the maximums and minimums are at, and if we want to know exactly what the curvature looks like, we need to do the first derivative, and then we also need to do the second derivative. So let's take a look at that. Again, here's our original function. We do the first derivative, we would get this. Then we're going to want to factor it. You'll notice we have x squared minus 8. So we can actually factor that into the difference of squares. So that'd be x plus root 8 and x minus root 8. And that's because we want it to be x squared minus something squared. So we can trade 8 for the square root of 8 squared. And then the difference of squares rule says that that will be x plus root 8 and x minus root 8. And now we know where the first derivative is going to equal 0. It will be when x is 0, or when x is either negative root 8 or positive root 8. We could make a first derivative chart and we could fill it out. And we would figure out that we are decreasing until you get to negative root 8. Then we'll be increasing all the way to 0, and then decreasing until you get to square root of 8, and then increasing afterwards. Now, normally increasing is going to be on a closed interval. As long as the function exists on that closed interval, it's usually going to have that bracket. You'll notice that we do not include infinity, and that's because infinity is just an idea, it's a concept, it's not actually an endpoint, it's not actually a number. Also, if you had an asymptote, then you also would not include the endpoint. So up top here, I just put examples for this function of where it is increasing and where it is decreasing. Usually when I sketch the function, what I'll do is I'll just draw the increasing and decreasing part first. So it might look something like this. Normally I would have it decrease until here, and increase till here, and decrease till here, and increase till there. So I haven't added the curvature yet. In order to do the curvature, I have to do one more derivative. When I do one more derivative, I'm going to start with this, and then I'm going to do the derivative. You don't want to start with all these factors, because then you'll have to do the product rule, and that'll be a disaster. Now, after doing one more derivative, you want to go ahead and factor it. This is probably the hard part. How do we factor this? We want it to be difference of squares again. So that's going to be the square root of 3x squared, and then minus, and then the square root of 8 squared. So the first thing is the square root of 3x, and the second thing is the square root of 8. So we do the first plus the second times the first minus the second. You can set each factor equal to 0, and your answers would be these two right here. Now, if you want to approximate those numbers, you can plug them into a graphing calculator and see what you get. Now, that's where your second derivative is going to equal 0. And again, you could fill out a chart for your second derivative, and you could figure out where your original function is concave up and concave down. That's how we can fix this graph. Instead of being straight lines, we can change it into concave up and concave down. Now, if you filled out your second derivative chart, you would notice that you would be concave down between B and C. Now, I want you to notice that that's going to be open interval. Concave up and concave down is always on an open interval no matter what. And we're going to be concave up everywhere else. So we're going to be concave up on the right over here. That would be from C to infinity. And we're concave up on the left over here. That'd be from negative infinity to B. And I'm just using the letter B because it's easier. You can see that B is negative square root of 8 over 3. Now, after using calculus to sketch my graph, I can see that there's an absolute minimum. It happens when x is a and when x is m. You'll notice this is an even function because the powers of x are even numbers. So the left side would match the right side exactly. There's also a relative maximum. It happens when x is 0. And we have two inflection points. There's an inflection point when x is b and also when x is c. I'm using the letter I for inflection point, and I'm using a capital M for either a max or a min. Okay, this one's going to be a little bit easier. You don't even need calculus for this one. We have the absolute value, and then inside we have this quadratic function. So the quadratic function without the absolute value will look something like this. Now you can factor it. You can see that it goes through x equals -1, and it also goes through x equals 5. Now that absolute value is going to take all of these negative values down here, and it's going to reflect them up. So it looks something like this. So the values that were 0 or positive are going to stay the same, and the values that used to be negative are going to reflect up, and they're going to become positive. So let's erase everything on the bottom, and now we're done. Now, what I want to point out is that the pink part is just the graph of y equals x squared minus 4x minus 5. And that's because the absolute value doesn't do anything to a y value that's already positive. I also want to point out that the blue part of the graph used to be negative, but now it's all positive. So really, it's going to be the function y equals negative parentheses and then x squared minus 4x minus 5. So the blue part is the same thing as the pink. It's just reflected upside down, so we just add an extra negative in front of it. Now that's important in case we wanted to do the derivative, because when x is strictly less than -1, or when x is greater than 5, we're just going to do the derivative of the red one, and that'll give us 2x minus 4. If I want to do the derivative of the middle, that's the derivative of the blue one, so that's when x is between -1 and 5. That derivative is going to equal -2x plus 4. So when we do a derivative of a function that contains an absolute value, we usually break it up into a piecewise function. In this case, it was the red and the blue. And that way the derivative is really easy to do. I want to point out that this function is not differentiable when x is equal to -1 or when x is equal to 5. That's pretty easy to see that the slope from the left is negative over here and the slope from the right is positive. So at that spot, the derivative is not going to exist. When x is 5, you can see that the slope from the left side is going to be negative and the slope from the right is positive. So again, at that spot, the derivative will not exist. Okay, this one's kind of a tricky little puzzle here. You have this parabola. The coefficients are a, b, and c. We have a picture of this parabola over here. We can see that it's been shifted right 1 and it's been moved down 4. The question is, what is the value of the a, the b, and the c? And all we have to figure out is if they are positive or negative. Okay, because we have so many letters, we have an A, we have a B, and we have a C. One of the things we can do is we can do the second derivative and it will get rid of the B and the C. So here we go, here's the first derivative, and then there's the second derivative. Now, based on this picture, we can see that we are always concave up. So we would expect our second derivative to be positive, so we're going to put greater than 0. And if we divide both sides by 2, we're going to get that A should be greater than 0. So we already have our first answer. Let's put a box around that. There we go. We know that a should be greater than 0. Another thing we know by looking at this graph is that the derivative is equal to 0 when x is 1. So we can take our original function, we can do the derivative, and we can set it equal to 0, but remember, that's when x is 1, so we're going to have to plug a 1 for the x. And that gives us this equation right here. We know that 2a plus b is going to equal 0. So then b is going to equal -2a. Now, if a is positive, then b is going to equal -2 times a positive number. So that means b is going to be negative. Okay, so we're going to choose b is less than 0. Put a box around it. Now for the value of c, that's just the y-intercept. We can actually see what it is. We'll go ahead and put a point there. There we go. So the c looks like it's equal to -3. So that means it's negative. Let's put a box around that. We'll say c is less than 0. Okay, let's put our 3 answers right here. Now, if you look at the bottom down here, I wrote that -b over 2a was the x value here. So yes, there are other ways to figure this out without using calculus. But in this example, of course, this is a calculus class, so we're going to use calculus to figure out our final answers. So our final answers are that a is greater than 0, and then b and c are less than 0. Okay, for this example, they want us to sketch the graph of f. It says if we have these 2 points, so 2, 2, and 6, -3. You can see that I plotted those here. There's 2, 2, and there's 6, -3. Now, the only way I'm going to be able to sketch this graph is by looking at over here, we have a graph of f prime. So that's where I'm going to get all my information from. First, let's look at increasing and decreasing. So f will be increasing when f prime is positive. So that's where f will be increasing. And then f will be decreasing when f prime is negative. So the blue part is where f is going to be decreasing because that's where f prime is negative. Again, here we're just looking at where f prime is above the x-axis or below the x-axis. and that's where f prime is either positive or negative. I also want to point out that f prime is equal to 0 when x is negative 2 and 6. So those are like your critical numbers. That's where we expect to have a tangent slope of 0 on the original function f. Again, the original function is going to increase until you get to x equals negative 2. The actual height doesn't really matter. Just make sure that you are increasing until you get to x is equal to negative 2. Then we're going to be decreasing until x is equal to 6. So that's going to look something like this. Now I want to make sure I connect those lines. Now there is something important happening here that I haven't talked about, and that's that the function f prime looks like a parabola. So f prime is a parabola, it's some kind of x squared function. So that means the original function is going to be some kind of x to the third function. So that's why my function f must be a smooth continuous function. Now it kind of looks like we have a sharp corner right here, but I'm going to fix that later. Right now all I'm doing is increasing and decreasing for the function f. Remember, this part over here is where f prime is positive. So after x equals 6, our original function should be increasing. So here we go. Just make it increasing on the original function f. Okay, now I need to figure out concave up and concave down. Remember, if f double prime is positive, then my original function is going to be concave up. And if f double prime is negative, then my original function is going to be concave down. So I need to find f double prime. I don't have a graph of f double prime, I just have a graph of f prime. Now remember, f double prime is just the derivative of f prime. So I need the derivative of f prime. Now the derivative of f prime is just going to be the slope of f prime. Now you can see the slope of this graph is going to be negative until you get to x is equal to 2. Then the slope of this graph is going to be positive afterwards. So that means my original function is going to be concave down until you get to x is equal to 2. So my original function is going to look something like this. Now remember, we changed from increasing to decreasing at x is equal to negative 2. So I need to make sure that my maximum happens at x is equal to negative 2. But I still need to be concave down. Let's try to fix that a little bit better. And let's put a point at x equals negative 2. And notice when x is greater than 2, our original function is going to be concave up because the second derivative is positive when x is greater than 2. So let's do that. Now remember, the minimum still has to be at x is equal to 6. So let's try to fix it a little bit better. Something like this is okay. Now I do want to point out there are 2 points on this graph that cannot be moved. When x is 2 and y is 2, that point cannot be moved. That point turns out to be an inflection point. Also, this point down here, when x is 6 and y is negative 3, this point can also not be moved. So I need my graph to be a little bit lower. Let's move it down. And now we can erase all those straight lines. Let's make sure everything is continuous and connected, and let's put arrows on the ends. Now remember, this is just a sketch, so it's not going to be perfect. Also, the height is not that important. This function could be shifted up or down. The only thing that cannot be changed is this point right here and this point right here. And that's because the original problem said that f of 2 had to equal 2 and f of 6 had to equal negative 3. Otherwise, this function can go as high as you want or as low as you want. Now, there are some answers that we need to fill in on the right. Where is there a relative max? Well, the relative max is right here, and it happens when x is negative 2. They just want the x value here, so we're going to say at x equals negative 2. Where is there a relative min? The relative min is right here. It happens when x is equal to 6. They just want the x value, so I'm just going to put 6. Where is your function increasing? Well, we are increasing before you get to negative 2 and after 6. So we're increasing over here, and we're increasing over here on the outsides. So we're going to have 2 answers for increasing. Again, it's not very clear. They're talking about the original function. This is where the original function is increasing. There we go. So our original function is increasing from negative infinity all the way to negative 2, and from 6 to positive infinity. And anytime you have that infinity symbol, you do not want to include the endpoint, so we want to put round parentheses on that. Okay, there we go. And our function is decreasing in the middle, so that would be from negative 2 to 6. Now remember, we did have one inflection point. Our inflection point is this yellow point here in the middle. So the inflection point is going to be at x equals 2 and y equals 2. On the right, they just want to know the x value. The reason why we also know the y value is because that point was given. Remember, there are only 2 points on this graph that we know for sure. 2, 2, and 6, negative 3. Everything else, all we know is just the x value. So I'm going to say the inflection point was at x equals 6. You'll see that we are concave down when x is less than 2. So we can fill that in. We're concave down from negative infinity to 2. We're concave up when x is greater than 2. So we can say from 2 to positive infinity. And that's it. That's how you would sketch the graph of f given these 2 points and given the graph of f prime.